Gool, who will talk about aperiodic monoids via saturated models.
Yes, thank you. Pro-aperiodic monoids via saturated models. Last talk of the day. I'm doing this, this is joint work with Ben Steinberg in New York, where I'm currently a Marie Curie Fellow. And I'm really happy to present this work here. It's about logic and computation, at least. Maybe you can tell me where the symmetry is. So, in the theory of regular languages of finite words, pro-finite monoids, you've probably heard, are useful canonical objects. And as I'm very grateful, Daniela already explained earlier today, such monoids are stone dual spaces of certain Boolean algebras. So any pro-finite monoid is in particular a stone space. And these Boolean algebras, you may think of them as Boolean algebras of languages, but you may also think of them as Boolean algebras coming from logic, certain logical theories. I will explain this a little bit better in the rest of this talk. But the question now is, well, if these pro-finite monoids are just spaces coming from logic, then we should be able to use logic to analyze those pro-finite monoids. And that's what we're starting to do here. In this talk, we'll just focus on first-order logic. I don't think that's a completely necessary restriction, but that's where we're most comfortable with doing model theory. Okay, so that's why we're doing first-order logic for now. So then there's this classical theorem that a language, I'm always talking here about languages of finite words, a language of finite words is first-order definable if and only if its syntactic monoid is finite and aperiodic. In other words, it's recognizable by a finite aperiodic monoid. I'll denote that class just by a boldface A. And then actually, if you think a little bit about this, what this theorem says is that if you assign to every first-order sentence the language that it defines, that is simply an isomorphism between the Lindenbaum algebra, the algebra of sentences up to equivalence, and the algebra of languages recognizable by an aperiodic monoid. Okay? So star-free languages, aperiodic recognizable languages, that Boolean algebra is just the Lindenbaum algebra of some first-order theory, namely those sentences which are true in all finite A words. Okay? Up to that theory, you look at all the sentences, that's the same Boolean algebra. So if you now take stone dual spaces, what is known from the theory of stone duality is that this notation denotes the free pro-aperiodic monoid. That is the stone dual space of the recognizable languages, the aperiodic recognizable ones. But since that Boolean algebra is also the Lindenbaum algebra of this theory, the dual spaces are the same. Okay? So if you read this equation, it tells you that there's a way to view the free pro-aperiodic monoid, a structure that's been studied a lot in monoid theory, to view it as the dual space of a certain logical algebra. Okay? And that's kind of the starting point here. So we can analyze the free pro-aperiodic monoid as a dual space of a Lindenbaum algebra. So let's look a little bit about what this dual space of a Lindenbaum algebra is. This is a well-known thing in logic. If you have any first-order theory whatsoever, then the points of the dual space of the Lindenbaum algebra, those are just the complete theories that extend your theory. Okay? Just in the sense of usual logic. They're also the ultra-filters of the Boolean algebra, right? That's the same thing. Another way to say it is, if you think more semantically, if you don't want sets of sentences but you want actual models, you could say, well, a complete theory, it's consistent, so it always has a model. It has a lot of different models. So I can regard one complete theory as a whole elementary equivalence class of models with that theory, right? It's the same thing. So the points of this space are elementary equivalence classes of models of T. And then what is the stone topology? It's simply the logical topology. So for any first-order sentence, I can look at what I call phi hat, which is the set of those classes of models where that sentence is true. Okay, that's a basis for the Clopen sets for my topology. So in particular now, applying this principle to the theory of finite words over a finite alphabet A, that's what this space here looks like. So the free pro-aperiodic monoid over a finite set A can be viewed as the space of elementary equivalence classes of pseudo-finite words, where by pseudo-finite word I mean a model of this theory, TA fin. That's some stone duality yoga essentially, but now how to use this, okay? So this is just a space for now. I just have a space underlying this monoid. And the space underlying that monoid, its points are just elementary equivalence classes of models. But that means I should be able to multiply such models, right? Because it comes from a monoid. And I should be able to do anything I can do in the free pro-aperiodic monoid. I can ask, well, what am I actually doing with those models? If I can describe an operation on those models, it should be invariant under elementary equivalence, hopefully, right? So that it actually becomes a well-defined operation here. So it kind of gives you a different way of viewing the free pro-aperiodic monoid. And in the last part of my talk, I will tell you a bit about how to use that to actually get some insights about the free pro-aperiodic monoid. So let me now zoom in a little bit more on what these models are, okay? So I will call, in this for the purposes of this talk, I will call an A word a structure in this first order signature LA, which just consists of a binary relation, which will be the order, and then predicates for every letter, okay, as you're used to when you're doing logic over words. So then an A word just means a discrete linear order with endpoints, and the predicates form a partition. A pseudo-finite A word is a model of the theory of finite words. So this notation suggests that that's a special kind of A word, right? And it's actually true because this theory itself is not finitely axiomatizable. It's not enough to just say, oh, I have a discrete linear order where the predicates form a partition. Yeah, there's a lot more that's true about models of the theory TA fin. A word is, here's a way to describe it, a word is pseudo-finite if and only if every first order formula that is true somewhere in the word, okay, I have a first order formula with a parameter, if it's true somewhere, then it's true for a first time. That's a property that an A word could have or not have, and if it has it if and only if it's pseudo-finite. So it's a model of the theory of finite words. So the typical example is a word like this. Start with the order of the naturals labeled by A, and then the reverse of the order of the naturals labeled by B. Okay? There's no first occurrence of a B here, so it's not pseudo-finite. It is a legal A word, but it's not a pseudo-finite A word. And now, actually, for most of this talk, I don't need to know that the word is pseudo-finite. I can do a lot of what I'm going to do. So the pseudo-finite words form the free pro-aperiodic monoid. The A words up to elementary equivalence form another pro-aperiodic monoid. It's much bigger than the free pro-aperiodic monoid, but I can still do a lot of the things I can do with the free pro-aperiodic monoid with that bigger monoid. So in particular, if you take any two A words, you can concatenate them, right? You just put them next to each other very concretely as models. And this operation, as is well known, respects elementary equivalence. If you do this to two pairs of elementary equivalent words, you concatenate them, the result is still elementary equivalent. And that is how this space of models is now a monoid as well. And you have to check that the operation is continuous, actually. Another way to see it, if you don't like topology, is to go to the dual space and go to the Lindenbaum algebra. There's a corresponding operation to this monoid multiplication on the Boolean algebra. As usual with stone duality, everything you have on one side, on the space side, it translates to something on the Boolean algebra side. Here, the corresponding thing is what's called a residuation operation. And this is maybe a nice exercise. If you have two first order sentences, then there always is a sentence that defines the following language, the language of those finite words, such that if you take another word that satisfies psi and you multiply it on the right, you get a word that satisfies phi. Okay? That is a new language that I'm defining, and it's still first order definable. if the other two are. Actually, you can say something much more general. If you, instead of concatenating words, you can just substitute words into words, right? You know this about finite words, but the same goes for pseudo-finite words. So if you think of a pseudo-finite word, it's a model, or even just for any A word as I've defined it, it's a model with a discrete order. If I label it by letters, and now I choose, for each letter I choose another word, then I can plug it in. Yeah, you have to define it properly, you take the lexicographic order, etc. But I think the idea of what the substitution should be is clear. And then this, so any assignment of words, of letter, from the letters of this alphabet B to classes of words in the alphabet A actually gives me a well-defined substitution for any word over B to a new word over A. Okay, so this is, again, you have to prove that it respects elementary equivalence, etc. So as I mentioned, there's actually a larger pro-aperiodic monoid where all of this takes place. So if you just look at the theory of A words and you play the same game, you look at the classes of models of this theory, let's call that pro-aperiodic monoid that we get lambda of A, lambda to indicate linear orders. Then the concatenation and substitution operations are well defined on A words. This lambda of A becomes a pro-aperiodic monoid, and it contains the free pro-aperiodic monoid, which were just the pseudo-finite A words, as a closed submonoid, and moreover, the complement is an ideal. So by multiplying non-pseudo-finite things, you always remain non-pseudo-finite. Okay, so now I told you I want to use some techniques from classical model theory to analyze the pro-aperiodic monoid. So far I've just shown you that the free pro-aperiodic monoid can be viewed as a monoid of models. But now we're going to use, in particular, saturated models to have a really nice, easy combinatorial way to look at those models and look at the corresponding elements of the pro-aperiodic monoid. So for that, I recall a little bit of model theory now. I won't recall the general definitions. I will just tell you what they mean in the case of finite words. Okay, so it's a very reduced view of classical model theory. So a type that would be called a complete one type in model theory is just a triple where I have two A words and a letter in the middle. And the type space is this product here. Why is that a type? Because essentially if I have an A word and I have a position, I can look at the theory of what happens to the left of that position, the theory of what happens to the right of that position, and what letter do I have. That completely describes the whole first order type of that word with a marked position, right? And now that's the type realized in a word. Now we call a type consistent if it's realized in some elementarily equivalent word. Okay, so it may not be realized in the word. In fact, a word is what corresponds to weakly saturated if it actually realizes all the types that are consistent with it. We'll have an example on the next slide, because now a word is omega saturated if this holds hereditarily. So that's again omega saturated. There's a model theoretic definition of it. But here it amounts to saying that as soon as you choose an interval, so you choose two positions and you look in between those positions, that should be weakly saturated. That is equivalent to being omega saturated, which would in model theory mean you mark a bunch of positions, but then you can look in each interval. Okay, so now from model theory, any elementary equivalence classes actually contains an omega saturated model. So we can actually assume that the points of this pro-aperiodic monoid are just in each class I choose an omega saturated one if I want to, right? So in the one letter alphabet, what do all the saturation notions mean? Well, first of all, I can look at the word which is just omega and omega reversed. That's not even weakly saturated because there is an elementary equivalent one where I put the integers in the middle. And that one I cannot realize by taking a type here, right? I cannot, because there's no middle in this one, so I cannot find a type here that's that has the type that I would get if here in the elementary equivalent model I choose a point in the middle. I see something infinite on the left and infinite on the right in this model. So this model actually is weakly saturated. Any type that I can realize in the class is already realized here, but not every interval is weakly saturated. To get that every interval is weakly, because I might take, if I'm unlucky and I pick a position here, then the interval on the right is just the interval on the right is a finite word. I guess I have to take a word here, a point here, right? And then what I get, if I look to the left of that point, I get this one, which I already told you isn't weakly saturated. So now, finally, if you iterate adding the integers in the middle, you get densely many copies of the integers, this ordinal here, so this means the dense linear order countable, and this means the integers ordinal product, and I take a beginning and an end, then I have an omega saturated word. Okay, so this is just for the one-letter alphabet. In more letter alphabets, it becomes more complicated what these saturated models look like. Okay, but I, at least for model theory, know that I always have them in every class. And now kind of an important fact that makes the machine work is that if you choose omega saturated words and you substitute them into omega saturated words, the result is still omega saturated. In particular, if you concatenate, I didn't mention this, but concatenation is a very simple substitution into the word 0, 1, or AB, yeah, where you put something in the first place, put something in the second place. And power by this special omega saturated linear order rho, that's also a kind of substitution, because if I take that order with all the time the same letter, and now in that letter I put no matter what word I want, then I get the power of that word, right? I get that word repeated rho times. So all of these things, if I start from omega saturated words, I obtain omega saturated words. So that's the model theory machinery that we're using here. And proving this theorem you can nicely do using the stone topology on the space of models and the fact that substitutions are continuous, and it's actually kind of a proof easy proof once you realize what all these things mean topologically. So now from this fact that I have saturated models in every class, I can recover some facts that were known about the free pro-aperiodic monoid. In fact, now I can prove them for that larger pro-aperiodic monoid, lambda A. For example, a monoid is called equidivisible if that quasi-equation there holds. It may be at this time of day that it's not that easy to parse, so it's easier to just draw a picture. If I multiply a word u with a word v, and I multiply a word u prime with a word v prime, and the result is the same, then it must be the case that there is actually a word, which will be this word x here. So sorry, here was u, here was v prime. Here's a word x, so that if I do u times x, I obtain u prime. And if I do x times v prime, I do v. Okay, it's kind of an obvious property if you are thinking of finite words, right? And now this monoid of all the A words up to elementary equivalence is also equidivisible. And the proof is, well, take their product and now pick for that product a saturated model. You know that it exists from model theory. And then in that saturated model, you know that all the types you want that might happen in elementary equivalent models are actually realized in that word. So now you draw that picture, okay? So you draw that picture about the word W. Pick a model which is saturated, and you know that both this gluing position here and this gluing position here are realized. And now I just take the class of this word. Okay. The way this, of course, these kind of proofs, so this is in fact known to be true for any pro-finite, I think even for any compact monoid. But the way it would usually be proved is by taking sequences, taking their limits, and showing that everything works. Here I have a kind of the proof you think of in finite words, you can basically copy it and justify it by using omega saturated models. So now, as a further, more advanced application, I won't show you all the details of this, I think, but if I have a substitution, okay, from this big model of all the B words, or big monoid of all the B words to the monoid of all the A words. Suppose I choose for every letter a class U of B. And suppose that what I'm going to do is I'm going to analyze the factors of a substitution. So I take a word V, I substitute into V, and I take a factor W. So W, if I multiply it in the right way on the left and on the right, then I get the result of substituting into V. Then what I know is that I can choose omega saturated words in each of these classes. And the theorem tells me that if I choose for my indexing word V and for the words that I'm substituting, if for all of those I choose omega saturated words, the resulting word of substituting all this stuff is still omega saturated. In particular, what that means is that if I take any factorization by some word W, it's actually going to be realized in the result of substituting. So classifying factorizations, which if you were just thinking of this as some compact monoid might have been hard, now becomes just a combinatorial problem of classifying what the intervals in this very concrete model V, capital V, with all the models U, B substituted are. So just to show again in a picture how that would look, you have an indexing model V, which you know is saturated, and for each point here, you substitute another. So if this was a letter B, you substitute a word UB, and you do that for every letter. You get some big substituted model. And now you have some factorization. It might cut through some substitutions. But what you can now say is that whenever you take an interval here, it will be a suffix of one of the words you're substituting. Then it will be some interval here where I just substitute all the words I want. And then I get another prefix of the last word that I wasn't completely taking. That makes sense. So that way I can completely understand what all the factorizations of a substitution are. And using that kind of method, you can now prove, for example, a result by Almeida, Costa, and Zaitoun, that in the free pro-aperiodic monoid, if you take a prefix, a suffix, or a factor of an element that is given by an omega term, it's still given by an omega term. Where omega terms, if you start from letters, you can always generate with concatenation and doing idempotent power. That's what the omega stands for here. And the words that you get are a special sub-monoid of the free pro-aperiodic monoid. But if you take a prefix of such a thing, it may cut somewhere in the middle, and you may not know that you can still describe it with an omega term. But the theorem tells you it is true, and using this factorization, it's actually not that hard to show. So I think I'll skip the proof but in detail, but the idea is simply to analyze what the factors can look like, okay, in the concrete model. So you use here, in particular, in the case of the omega power, you use the fact that the saturated model for omega is this dense order with a beginning and an end, and you just cut it somewhere, and you see that all you can get is either an actual natural number, or again an infinitely many copies. Okay, then here's some advertisement. We have a preprint on arXiv for other things you can do with these techniques. So you can use it to analyze the structure of both of these monoids. You can prove things that were used by Ben Steinberg in collaboration with Henkel and Rhodes to analyze stable pairs. So they proved that, or I'm not sure if all of these results are theirs, but they used them in any case in that paper. So unambiguity of the L and R orders, the fact that the L and R orders are total on stabilizers. This is all in our paper, using these new methods. Also, to decide whether two omega terms are equal, there was a few years ago a proof, an algorithm by Huschenbett and Kuftleitner, who proved that if you interpret omega terms in the right way, then they are elementarily equivalent if and only if they are isomorphic. And actually, the way that they interpreted them, they didn't say that, but we realized that they interpreted them as countably saturated models always. Well, from model theory, countably saturated models are equivalent if and only if they are isomorphic. So there, one crucial part of their result becomes clear from model theory in this way. Then we looked at well quasi-orders of factors. Having a well quasi-order of factors is stable under substitution if you analyze the factors in this way. Having a regular language of finite factors is another property that's stable under substitution. And so in particular, omega terms, by induction, omega terms have both of these properties. And that's all I wanted to show you. Thanks.
Sort of question, comment. I guess you were thinking about deciding computational properties, like deciding MSO theory of such structures. And so if you go to a slightly higher level and you take the MSO profinite monad, so the normal profinite monad, then when appropriately formalized, MSO theory becomes undecidable. So which way do you think this is going to go here? What was your conjecture?
Wait, but for finite, I'm just doing finite words for now, right? So then MSO is just...
No, but your monoid contains, if you view it the model theoretic way, it contains infinite models. Omega saturate and so on, but they're infinite. So you could run MSO on them with standard semantics.
Yeah.
And then you could consider the problem given an MSO formula, is it true in a model of your form? And that
where you mean the more general models or the pseudo-finite ones?
The pseudo-finite
ones. In the pseudo-finite ones. I have no conjecture to make about that, but it's interesting.
So I thought you didn't think about that.
No.
That's, I think, very interesting.
Okay, yeah.
Well, we do have a reception waiting for us, so let's thank Sami again.